Okay, so it's talking about prisoners. They selected 33 prisoners diagnosed with this disorder, PTSD. 23 that were diagnosed with PTSD but had since been remitted. The ages and years at arrest yielded the summary statistics table to the right. So what are we looking at here? So we have two different groups here. We had a in the first group of 33, the average of the ones that had the chronic syndrome or disorder, their average age was 28.5. And then this group of 23, the average age was 21 for these 23 that had the remittent, like they got cured, right? So it says, do the data provide sufficient evidence to conclude that a difference exists in the mean age at arrest, their age at arrest, I see, with chronic versus remitted PTSD. So is there a difference between the mean age at arrest for chronic cases versus remitted cases? So what is our null hypothesis? Yeah, null hypothesis is always equals, right? So it's going to either be B, C, or D. And then if we want to say, it just asks, is the mean age at arrest different for chronic patients versus patients that have remission? So that they're different, right? So it's not saying one is greater than the other. It's just saying that the means are different. Okay, so we want that one. Okay, that's right. Find the test statistic, right? So the test statistic we're going to get from StatCrunch. Is there usually there's a link. Question help.
Yeah, and then StatCrunch.
Awesome. Usually there's a little icon. That's a new feature they have. All right. Okay, and so we're going to go, like I told you, we're going to go to stat, tstats, to sample with summary, right? We don't have data, we have summary. So we got sample mean 1, 28.5, sample standard deviation 5, sample size 33, sample mean number 2 is 21.2, standard deviation 7, size 23, and we're going to have non-pooled variances, and we want that the difference is not equal to 0. So saying that they're not equal is the same as saying that the difference is not equal to 0, so I think we got everything right. Our test statistic is 4.2955. How many decimal places do they want? 3. 4.296. Okay. The critical value then we're going to get from our t-chart, and we have degrees. How many degrees of freedom are we going to do? It's 37.19. We're going to round down to the nearest whole number, so 37 degrees of freedom. And we want 5% significance level. But this is a two-tailed test. So what's our alpha going to be? So you're going to look, because the
37 2.026.
we want 2.5% of the area there, 2.5% of the area there. And the t gives you this critical value. So you're going to do t of 0.025, and was it 37 degrees of freedom? For 37 degrees of freedom, and tell me what you get in the table.
2.026.
And so it's plus or minus alpha over 2. I'm sorry, one more time.
2.026.
3 decimal places. Okay, something's off there.
You have to enter in positive and negative. You have to put both
Comma. Yeah.
Ah,
So it's minus 0.26.
that's why you get multiple attempts. Figure things out like that. There we go. Okay, what's the conclusion? So our test statistic, 4.296. Our critical value is, so where does our test statistic lie? In the non-reject or the rejection region? Way up here. Way, 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 way up here. That's 4.3 standard deviations. It's like off the chart, okay? That's like off the chart. That's like 0% of the data would lie to the right of that. And 100% of the data, virtually 100%, lies to the left. Way off the chart. Reject or do not reject? Reject, big time. The data provides evidence or doesn't provide evidence? Provides. Okay, so on the test, this was, and then also on we did the in-class sheets on Wednesday. There's still confusion about this. When you reject, that means that there is sufficient evidence against the null hypothesis. When you don't reject, that means there's not sufficient evidence against the null hypothesis. Those are the only two conclusions we'll ever make. You'll always put reject with there is evidence for something, and that something is to reject the null, that they're different or one's greater than the other. When we don't reject, it will always be the conclusion that there's not enough evidence. Okay, there was trouble on the test and on the sheets on Wednesday. So when we reject, we say, yes, we've got evidence to say the null hypothesis is not true. And when we do not reject, it'll always be, there's not enough evidence to say that the null is not true. Or in other words, the null still might be true. Okay, questions on this one? So maybe the difficulty came getting the plus or minus in there. All right, we're going to move on. Any questions on comparing two populations? Comparing two populations. Okay, so next set of stuff. Okay, so the next set of stuff is very pertinent, and it's called Inferences for Population Proportions. All right, and this is actually very pertinent with all the election stuff going on right now. Okay, this is exactly when they poll people, they take polling of percentages of people they're going to vote for a candidate or are favorable towards a candidate. This is exactly what we're talking about. So maybe we'll get some real world data on Wednesday after you've done the homework. We'll get some real world data and we'll see how this stuff is exactly what you see in the news and on the internet when you get these poll results. Okay. So here's the deal with this. So don't turn off your ears and your brain and write word for word. Listen to what I'm saying, and take notes that reflect that you're listening. Okay, so we have a population where every member of the population either has an attribute or doesn't. So there's only two possibilities for every member of the population. Okay, and so the population proportion P is the percentage of the entire population that has a specific attribute. Okay, and then we're going to take a sample of the population and we'll figure out what percentage of the sample has the specified attribute, and that will be p hat. So this little quiz here, 72% of 125 adults polled prefer vanilla over chocolate ice cream. Is that, everyone stop writing? Is that p or p hat? 72% of 125 adults polled prefer vanilla over chocolate ice cream. Is that p or p hat? I heard both. This is a p hat because it's a sample, right? We're taking a sample of adults, and we found out that 72% prefer vanilla. So that's a value of p hat, and that's equal to 0.72. 56% of all cars in the U.S. are imports. Is that p or p hat?
P.
This is population now, right? This is population, so then we'd say p equals 0.56. So if we're talking about inferential statistics, how do p hat, what's the relationship between p hat and p in the topic of inferential statistics? How are we going to use these numbers? Remember what inferential statistics was? Heather beat you out by a hair.
Using a sample to figure out what a larger population is going to do.
Right. So then how would you use the symbols p hat and p to
So if you're trying to figure out what P, like everyone in the U.S. is going to vote for, or from each state is going to vote for, you take a P hat of what each people prefer.
Right. So p hat is, we're going to have p hat is from a sample, right? So there's a sampling distribution. So every sampling distribution we've done so far is for the sample mean. We took samples, found the mean, and then we made a distribution of means of samples, right? To try to figure out what the population mean was. So now we have a new kind of sampling distribution, and this is a sampling distribution of sample proportions. So we take 125 adults in California, and we get that 72% of them prefer vanilla. And then we take 125 adults in the Northwest, Oregon, Washington, Idaho, and we get 0.69 prefer vanilla over chocolate. And then we go to the Midwest, and we take another sample, and we get 0.73. So we're making a distribution of sample proportions. And we're going to use that distribution to try to figure out what P is for the whole United States. What is the actual preference? What percent of adults like vanilla over chocolate? All adults. Okay, so this is a new kind of sampling distribution. Before, sampling distribution was get the means from all the samples and make a distribution. Now it's get the population or the sample proportion from every sample and make a distribution out of those. And then our goal is to infer about the population proportion, P. Okay, does the general idea make sense? So this is like polling statistics. So as it says, 750 registered voters were polled, and 32% have a favorable 32% had a favorable view of Trump or whatever the candidate is. And so they're inferring from those 750 adults what the whole population is in terms of registered voters and their favorability of Trump. Okay. All right, so this is the sampling distribution like I talked about. And so we're going to do the mean, right? So the mean of all the p hats is going to do what? It's going to equal p. And that's, so the mean of all the p hats is mu p hat, just like before. Instead, so before it was mu x bar, right? It was the mean of all the sample means. Well, now it's the mean of all the sample proportions, and that's always going to equal the true population proportion. And then the standard deviation of the population of the sampling distribution,
Sigma p hat.
right? And that's this easy formula. And then again, when n is large, yeah, so that this distribution is normally distributed. So this is our sampling distribution of the sample proportion. Which is normal for large n, and like greater than 30. So it's the same thing we did before, except instead of means of samples, it's the population proportion of samples, or the sample proportion of samples. And we make a distribution out of those. But everything else is going to be the same. We're gonna have confidence intervals, and we're gonna do hypothesis tests. Confidence intervals and hypothesis tests around to figure out what the population proportion is. You don't write this down, okay? So it's going to be the same thing. This is going to be our point estimate plus or minus a number of standard deviations times what the standard deviation is. This is the same thing we did before, but now it's just we have we're doing proportion of samples rather than mean of some attribute of samples. Okay, so let's look at this 11.13. We'll do this together. So a poll asked Americans whether states should be allowed to conduct random drug tests on elected officials. Of 21,355 respondents, 79% said yes. Okay, so we want to determine the margin of error for a 99% confidence interval. So we want to build, so we're basically building the 99% confidence interval. Okay, do we have a large sample?
Does large still mean more than 30?
Yeah, so this is huge, right? Huge sample. %79 said yes. So is that P or P hat? That's P hat. That's a proportion of the sample. And we want to build a confidence interval for the population proportion. So what is our point estimate for the population proportion? What's our best guess at what the population proportion is? 0.79. It's the only info we got, right? We only have one sample. We got 79% of our sample says yes, we should have random drug testing for elected officials. That's the best that we know. So we're going to come up with a confidence interval for P. And the center of that confidence interval is going to be 0.79. Okay, so if it's a 99% confidence interval, what percent do we have outside of our confidence interval? So if we think of it's like this, then what percent lies outside the interval? Total percent is 1. Well, the total percent outside of our confidence interval is 1. So on each side it is 0.5%, right? So 0.5%, which is what area? 0.005. Okay, so we're going to go to our Z chart. And we've done this in the past, but we'll just do it again for practice. We already, so we've done 99, 95, and 90, but just so we remember what we did, we're going to go to our Z chart now. We're going to go to Z chart, and we're asking Z of 0.005. Remember, because that's the area to the right. Chart gives area to the left. This is area to the right. So what are we going to look at in the table? We're going to look at what amount of area? Do you have a question?
0.005 half of 0.5.
No, so 1. So the total is 1. This is half.
Okay, yeah.
You see?
Yeah,
The 99% confidence interval means 0.5% over here and 0.5% over here. Are we good?
Yeah.
All right, so what number are you going to look at? This is saying we want the Z for 0.005 to the right, but the table gives areas to the left. So what are we looking at? What number are we looking at here? How much area? See, we want this Z value right here. So how much area lies to the left of that? Not 0.0 anything. This is 0.005 here. The table gives areas to the left. Did you forget all this? Okay, so we need, when we look in the table, we're looking for, it's going to give us this area. So what do we look for in the table? 995. Remember that? And this should be a familiar number. So you're going to look at the area 0.995 and get the corresponding Z value, which was what?
2.58.
Is this the one where it's like in between two? Let's get 3 decimal places. 2.575? 76?
76.
Okay, do you guys remember doing that? So for a 1%, or sorry, 99% confidence interval means 0.5% here and 0.5% here. So we want the Z value for an alpha of 0.005, or that's alpha over 2. So that's alpha over 2, because alpha is 1%. But the table gives areas to the left. So the area to the left, so that we have 0.005 to the right, is 0.995. So you look in the table of 0.995 and you get a Z of 2.576. So that means we're going to go up and down. We're going to go plus or minus 2.576 standard deviations. Okay? Now, what is our standard deviation for population proportion, right? What's our standard deviation for population proportion? That was the square root of P times 1 minus P all over N. Is that right? So what's our P? 0.79. 1 minus P will be 0.21.
Yes.
21,355. So this is similar to doing what? Standard deviation over the square root of n. Remember that? Standard deviation over the square root of n to get your sampling distribution. Standard deviation. So this is similar. Tell me what you get when you do that.
0.003.
0. Let's do one more decimal place.
1.
0031. Everyone in agreement on that? So this is our standard deviation for a sampling distribution of population proportion with this sample size. And what do we want? We want to go 2.576 standard deviations of these above and below to make our confidence interval. So we're going to go, let's go do it here. So what will this be? This right here will be 0.79 plus, how do we go? 2.576 of those above 0.79. So what do I do? 0.79 plus what? If I want to do 2.576 of these above 0.79, how will I do that? Yeah, so we're going to go 0.79 plus, no, 2.576. That's how many of these we want to go above 0.79, right? So we want to go 2.576 of these above 0.79. So it'll be 2.576 times 0.0031. And that'll give us the top of our confidence interval. Once you get a number, shout it out. 0.79. 0.798 pretty much?
Yes.
Okay. So what do you notice? Is this a wide confidence interval or narrow? Very narrow. Why is it very narrow? Our sample is so huge that we would expect that this is a very, very good estimate of the population proportion. Because we have such a huge sample, we can be confident that it's really close to 0.79, that we got a really good estimate. So our confidence interval is going to be really small. So then what is the lower limit? 0.782? Yeah, so it's like with such a huge sample, we can really pinpoint, we can really hone in on what the population proportion is. We're 99% confident that it falls between 78.2% and 79.8%. Okay, with a 90% confidence interval, okay, so meaning we'd be less confident. Would that be a wider interval or a narrower interval than 99%? So we're saying we're willing to be less confident about it being in the interval. Will that be wider or narrower? 90%. You think it's narrower? Does that make sense? Or do you think it should be wider? So if you widen it out, now you're less confident that the population proportion lands in that range. Does that make sense? Yes or no? Everyone, they're smiling. I'm going to make it wider. So suppose I make it like this. Suppose I make it from from 70%. I'm going to go from 0.7 to 0.88. Am I less or more confident that the population proportion falls between 0.7 and 0.88 than in this interval? Would I be less confident or more confident? More confident. If I extend it way out there, right, the further I spread it out, the more confident I am that I'm containing the population proportion, right? So less confident, a smaller confidence interval would mean a 90% confidence interval is going to be narrower or wider than this one. Okay, I just made a wider one here, 0.7 to 0.88. Think about this. More confident or less confident that the population proportion falls in this very wide interval? More confident. We're allowing for more possibilities. So this is a higher confidence. right? Higher confidence, like for instance, 99.9999999% confident that it falls in that wider interval. So if you make a lower confidence, does that mean a narrower interval or wider? Narrower, because a narrower interval, you're going to be less confident that the actual mean falls in there because you got less room. Okay, does it make sense?
Is the wider confidence interval the 90%? And then the smaller one is the 99%?
No, so just think about it. If you make a really wide, are you more confident or less confident that the population proportion falls in a really, really wide interval? More confident? More. Higher confidence. So if I do something like this, like from 70 to 88%, that's going to be much higher percent confidence. We're going to be very confident that it lies in a bigger interval. So a smaller confidence interval means, so for a 90% confidence, but less confidence, you're less confident if you narrow it in. If you want more precision on your guess, then you're less confident that it's actually going to fall in there. Is that better?
So,
I think people are confused with the percentages being how accurate it is. That's what I got confused.
But what is this percent about? It's how confident we are that the population proportion lies in the interval. Okay, so how confident. So you understand that a wider confidence interval means we're including more and more possibilities for what the population proportion could be. So we're more confident that it lies in our interval. But it's much less precise, right? So to have higher confidence, you have much less precision. Now you're saying, yeah, you're much more confident, but it could be it's a much wider range of values, so you're not sure of what it is as much. But you're more sure of that it actually falls in there. So if you make a smaller interval, yeah, that's more precise, but now we're less certain that we're actually going to have the value the population proportion that we're looking for. Still confused, or is it better? Okay, so they wanted the margin of error. Remember what the margin of error was? Same as before. So with all these numbers that we've written up here, what would the margin of error be, or how would you find the margin of error? And then this is like when you hear about these polls, these real world polls. They always say, this is the sample size was 800 registered voters, and the poll has a margin of error of such and such. They always say that. Aren't some of those?
No, I don't think so.
Sorry.
It's just an energy.
Oh, okay. Mixing cups. Just enough. Okay. So, margin of error. Remember what it was? Half the width, right? Half the width. So the margin of from there to there. Half the width of the confidence interval is the margin of error. So we already computed that. So where in our calculations did we already compute that? So in our calculations, that's part of our calculations. What is the margin of error in our calculations? It's what? It's how much we went up from 0.79 to get to the top. So what is that? This thing right here. That's the margin of error. How much we went up from 0.79 to get to the top of our confidence interval. So it's that number, whatever that turns out to be. Oh, 0.008. So it's z times sigma. It's z times sigma, or it's what? You could take the top of the confidence interval minus the bottom of, to get that whole distance, and divide by 2. Both ways are get you the same number, e. Okay, questions on... So what's the conclusion? We're 99% confident that between 78.2% and 79.8% of Americans think that drug testing should occur for elected officials. If we were only 90% confident, that'd be a smaller interval, right? Smaller interval. For a smaller interval, then we'd only be 90% confident. So why don't you guys do for your sheet, why don't you do the 90% confidence interval and the margin of error for 90%. And you'll see that that's even a smaller interval than this, right? Even a smaller interval than this. You don't have to whisper. I'll be right back.
It just has the. Yeah. No. Everybody is this because if you do 90 minus 1, you get 10. It's 2 to the right hand, be 5%. So 0.5. That's
It could be somewhere between these two, and we're a certain amount confident of that it's between those two. Other questions? Okay, so let's do hypothesis testing for this. So, again, we're going to have a two-tailed test, a left-tailed and a right-tailed. We're going to have a significance level. And this is the formula for our test statistic. And that's not bad. We could do that by hand, but we can also check it with StatCrunch or do it with StatCrunch. So this isn't. But again, what was our test statistic for sampling proportion for means, sample means? What was it? It was x bar minus mu over. So you see, it's very similar, right? It's like the value from the sample minus so actually you're not right. The hypothesized. So there's a hypothesized, and we take the difference between that and the sample over the standard deviation divided by square root n. So this is very similar, right? It's a very similar type of thing to get our test statistic. And again, our null hypothesis will be that p equals some value, right? And then the alternative hypothesis will be one of these. Okay, so now there's this condition we have to do this. Okay, and so I'm going to draw your attention to this. N times p naught and n times 1 minus p naught have to be 5 or greater in order for this hypothesis test to be valid. So there's a new condition on this in order for it to work. Okay, so can we give it a try?
Wait, why is that?
I don't know. I don't know that off the top of my head. I'd have to read in the. I'm sure it's in the book. We could read in the book. Oh, so this is basically what okay. So we can think about it. This is just basically about the size of the sample, right? So if we're taking some proportion of n, right? That's what these are. This is a proportion. So a proportion of n has to be at least 5. So this is about the sample being large enough. Right? Because this is taking what? This is taking some fraction of n, and this is also a fraction of n. So this is about n being big enough. Remember, we don't get good results when samples are small. So that's what it's about. Okay. I think we can go right to the examples. I don't think we need to do that. Let's try 11.66. Okay, so we got a telephone poll of 758 Arizona adults who celebrate Christmas. That question was asked: in your family, do you open presents on Christmas Eve or on Christmas Day? 394 said they wait until Christmas Day. Okay. So let's get the data here. What is n? 758. Okay, and then it says 394 said they wait until Christmas Day. So what is p hat? He wants 394 divided by 758. He likes it. We want the what? We want the proportion, the percentage of all who sampled that wait until Christmas Day. So yeah, it's going to be 394 over 758. And what is that?
51.98 or 0.519.
So that's the sample p hat. That's our sample proportion. 0.5198. Okay, so at a 5% significance level, did the data provide sufficient evidence to conclude that a majority, more than 50%, of Arizona families who celebrate Christmas wait until Christmas Day to open their presents? So we're going to have a null and an alternative hypothesis. The null hypothesis is that the population proportion is equal to something. always equal, right? So our null hypothesis is always about some things being equal. So equal to what? So what is our null, like what is our baseline for comparison for population percentage? Or maybe we'll try the alternate first. So do the data provide sufficient evidence to conclude that a majority, more than 50%, celebrate Christmas, wait till Christmas Day? So the alternative is that P is what? Greater than 50. Therefore, the null is equals 50. Same thing that we've always done, right? Same thing we've always done. So in this sample, we got a sample proportion of 0.598, 5198. Is there sufficient evidence to say from that? Is that sufficient evidence to say that more than half, the majority of Arizonans, wait till Christmas Day to open their presents? We got to do the test, right? We got to do the test. It's greater, but is it enough greater to say, yeah, there's evidence to suggest that it's more than half? We got to do the test. All right, so how do we do the test? We need a test statistic, and we need something to compare it to. So, what is our test statistic? It's going to be the difference between, right, 0.5198 minus divided by square root of 0.50 times 1 minus 0.5, and that was that divided by then 758? Does that agree with the formula we had on the previous page? Does that agree with what we wrote? Okay, crank it out. What do you get? As soon as you get it, shout it out. So you gotta make sure this is all under the square root. Like maybe do the square root first. And get that number and then divide by what? 0.0198. Sounds like a reasonable number. Does somebody else get that? What did you get, Abby? What did you get? Well, people are getting 1.090. You too? 1.09. Okay, so if we're doing a 5% test, right? We need our 5% means this is 5% of the area. So we're going to do z of 0.05 because it's a right-tailed test. So what are you going to look for in the table to find z of 0.05? What area? 0.950, right? 0.950. And again, this should be a familiar number. What is this? What is it? 1.645. All right, so our critical value is 1.645. Our test statistic is 1.090. Now, we didn't check the greater than 5 thing, but we have a huge sample, no problem with that, right? Because so 758 times 0.5 and 758 times 1 minus 0.5 both have to be greater than 5. We're fine with that. They're way bigger than 5, so no problem. Okay. Our critical value is 1.645. So does our test statistic line the reject or the non-reject region? Non-reject, right? So we're not going to reject the null because there's evidence or because there's no evidence, not sufficient evidence. If you're not rejecting, that means there's not sufficient evidence. There's not sufficient evidence to say that a majority of the Arizonans open their presents on Christmas Day. In other words, this isn't big enough. This isn't big enough compared to 50% to say we have sufficient evidence. We may have just gotten a sample that's slightly greater than 50, right? So here's what we would write. We do not reject. There is not sufficient evidence to say that a majority or more than 50% of Arizonans open presents on Christmas Day. Arizonans who celebrate Christmas. It still could be 50%. There's just the evidence doesn't support at a 5% significant level. That's more than half. Questions on this example? Okay, so you're going to do this one. Now I want to point out that this is, look. What kind of, is this going to be a two-tailed? It says the percentage of families with incomes below the poverty level was lower among those living in Wyoming than among all U.S. families. Is that going to be a left-tailed, a right-tailed, or a two-tailed test? Right. Right. You're going to have some null hypothesis amount. Okay, and then you're going to have down here, you're going to have your critical value. Is that critical value going to be positive or negative?
Negative.
Negative, okay, so your critical value is going to be negative. Based on an amount of area over here. So make sure your critical value is negative, and you're comparing over here on the left side with negative values. Your test statistic and your critical value should be negative for a left-tailed test. The question is the test statistic more negative than the critical value, or is it less negative? That will determine if you reject or not reject. Okay, go. We're going to finish this one. You guys do this on your sheet. You can work together. Oh, so yeah, let me give you the roadmap of what you're doing in this problem.
Oh no.
I'll just write it out. And you can put it in your calculator. So you need parentheses. And then you do 0.098. And then do parentheses. 1 minus.
Okay, so in red, I've laid out the roadmap here for what you're putting on your sheet. The null and alternative hypothesis, find the critical value and test statistic, make a sketch of everything, sketch everything, the regions, the critical value, the test statistic, make your conclusion, and write the sentence. Write the sentence of explanation. You got 5 minutes.
And